Okay. Well, welcome to Elementary Linear Algebra. So this is the first video in the Math 2200 course. And linear algebra is a very broad subject and very interesting subject. A lot of applications for this, and you can study linear algebra for as long as you want to study it. As a matter of fact, there are graduate courses in this topic. But this is elementary linear algebra, and so we're going to just kind of do brief introductions on a lot of topics and get kind of the language down. The first couple of chapters will probably seem familiar because some of this stuff you will have seen in algebra, college algebra, pre-calculus. And then once we get to maybe chapter 3, definitely chapter 4, we're going to get into things more of the linear algebra topic, I guess. And the more interesting things, the more useful things, and all that. But kind of need to get started with some basics, and so that's what this first section is. So the first section is on systems of linear equations, which for sure you've seen in algebra. Usually in algebra 1, algebra 2, or college algebra, you will see where you have two linear equations and you have to solve for x and solve for y and that kind of thing. So that's kind of where we're starting. And then as we move along, of course, it'll get more interesting, more involved, and different more interesting topics. So first of all, let's start with what is the definition of a linear equation. So a linear equation in variables. So in algebra 1, algebra 2, pre-calculus, a lot of times you'll see these in 2 variables or 3 variables. You really have as many as you need, or as many as there can be. So we'll just say in variables. In is just some positive integer. So as the form, we have a1 x1 plus a2 x2, so on all the way up to an xn equals b. So all of these a terms are or a coefficients are real numbers. The constant term b over here is going to be a real number. The first one, a1, is the leading coefficient, and then x1 is the leading variable. Not super important, but that's what they're called. So what makes this linear? Let's see a few examples here, and we'll talk about why these are linear or why they are not. So this first one, 3x plus 2y equals 7, this one is linear. And so really what you want to look for with linear is you're not super worried. I mean, we're not going to see, it says they can be real numbers. So, in order to not be a real number, it probably should be an imaginary number, and we're not going to see imaginary numbers here. So, but the coefficients need to be real numbers. The more important thing to look for is we don't have any x squareds, x cubes, square roots, anything like that. No x's in the exponent, that kind of thing. So this one is linear, and we could solve this. I mean, this is fairly obvious, so we could solve this and put it in y equals mx plus b, and then it's very clearly a linear equation. What about this one? So here we have 1/2 x plus y minus pi z equals square root 2. So all the coefficients are fine. These are all real numbers, even if pi and square root 2 are imaginary, or not imaginary, irrational. They're still real, so that's okay. And then the other thing, again, we have x to the first, y to the first, z to the first. And of course, in variables, we could have as many of these as we need. In this case, we have 3 variables, but this one is also linear. Then moving along, we have sine of pi x1 minus 4x2 equals e squared. Now, of course, sine of pi is just 0, so really we don't even need that term. So this is fine. 4, of course, is fine. E squared is irrational, but that's fine. And then again, we have no exponents on the variables, so that's good. So this one is linear. Now, I will point out we had x and y here. We had x, y, z here. Here we have x1, x2. Most of the time in this course, probably we're going to use x1, x2, x3, or however many we need instead of x, y, z, because once you get to z, then you go maybe w, and then once you get past w, where do you go after that? So you run out of letters, I guess, if you're using X, Y, Z, and so on. So most of the time we'll probably use X1, X2, X3, and whatever else we need. All right, so these three are linear. Now, what about this one? X times Y plus Z. Now, this one is not linear because of this part. So non-linear. You cannot multiply two variables together. So non-linear in that case. E to the X minus 2Y equals 4. E to the X is non-linear. So you cannot have a variable in the exponent. And then we have sine of x1 plus 2x2 minus 3x3 equals 0. Now this one, obviously this is a trig function, so that makes this one nonlinear. So we're always looking for, so up here it's okay because sine of pi is just a coefficient. That's just a number, and it could be sine of anything. It'll always just be a number. But you cannot take sine, cosine, tangent of a variable. You cannot have a variable in the exponent. You cannot multiply variables together. All right. Solutions and solution sets. So again, this is something you would have seen in algebra class, but we'll go over this quickly. A solution of linear equations, a solution of a linear equation in n variables is a sequence of n real numbers. So in other words, if n is 2, this is an ordered pair. So you'd have, say, 0, 1. You'd have an ordered pair where 0 satisfies the x, 1 satisfies the y. If you have n variables, you're going to have n real numbers in this sequence and not just 2. So it satisfies the equation when you substitute the values. The set of all solutions of a linear equation is its solution set. So to describe the entire solution set of a linear equation, use a parametric representation. And we'll see what that is in just a minute. So let's look at this number 2. We have 3x plus 2y minus z equals 3. And so I'm sure you're aware that when you have one equation with multiple variables, you can't really, there's not just one solution. Either you have no solution, possibly, or you have infinitely many. For instance, if we plug in, say, 1, 0, 0 into this equation. So x is 1, y is 0, z is 0, that will work. So there is a solution. If we plugged in, let's say, 2, and then 2, so that would be 6, plus 4 would be 10, and then this would be 7. That would be another solution. And we could come up with more. So 2, 2, 7, another solution, and on and on and on. So how can we write the solution set? So these are part of the solution set, but clearly we could just pick any two numbers for x and y, and then you could figure out what z needs to be, and that will give you a solution. So just to give you another one, pick 1 and 1 for x and y, that gives us 5. That would mean that z needs to be 2. And so there's another solution to this equation. So how can we do this? Let's let z equal t, and this is the parametric representation. Z equals t, and let's let y equal s. And then we can substitute and then just solve for for x. So 3x equals negative 2s plus t plus 3. So we're just moving these two over. And then divide by 3. So we get negative 2/3 s plus 1/3 t. And then 3 divided by 3 would be 1. And so now we could let s and t be whatever we want. Here I was letting x and y, just choose x and y, and then we figure out what z is here. And it doesn't matter what you pick, honestly. You could pick any of the two variables because we have two extra ones. And pick any two numbers for s and t or y and z, whichever one you want to call them. and then we can figure out what x needs to be. So if we let, say, s equals 0 and t equals 0, then plug in 0 and 0, and then x is 1. And of course, that's the one that we got here. If we let s equal 1 and t equal 1, then we get negative 2/3 plus 1/3. That's negative 1/3. And then plus 1, that would be 2/3. So then x would be 2/3. And then that will also solve the equation. So the solution set would be x equals negative 2/3 s plus 1/3 t plus 1, y equals s, and z equals t. And so there is our solution set. And so that's a parametric representation. So whenever you have more variables than equations, so we're going to talk about systems of equations here in a minute. Anytime you have more variables than equations, you're going to have this parametric representation. So either you have no solution, possibly, or you have infinitely many solutions. All right, so let's talk about systems of linear equations. So that's just where we have m, or however many m linear equations in n variables, is a set of m equations. So each of which is linear in the same n variables. So we may not have, so some of these coefficients could be 0, so maybe they don't all show up, but we consider them all as far as the system goes. So a system of linear equations is also called a linear system. A solution of a linear system is a sequence of numbers, or ordered n tuple instead of ordered pair, ordered triple. That is a solution of each equation. So in other words, this set of numbers has to satisfy each of these equations. All right, so let's do something that you probably did in Algebra 1, Algebra 2, college algebra. Let's solve these, and maybe we'll do these a couple of different ways. So let's look at this first one. So you have x plus y equals 3, x minus y equals negative 1. So one way to solve this is, if you notice, we have the plus y and the minus y. So we can add these two equations. So let's just add this equation plus this equation. So we get x plus x is 2x. Y minus y will go away. 3 minus 1 is 2. So that gives us that x equals 1. And now we can back substitute. So plug in 1 into either of these equations. Doesn't matter which one. We'll use the first one. And we have 1 plus y equals 3. So then y equals 2. So then the solution to this system is 1, 2. There's not going to be any other solution. If you only had one equation, of course, you can have infinitely many. But if you have two equations, you still could have infinitely many, which we'll see in a minute. But you could also just have one. So let's graph these. And maybe the easiest way to graph these, you could solve these for y, get negative x plus 3, and then get y equals, what would that be, x plus 1. And you could do it that way, or you could figure out the x-intercept and the y-intercept. So the x-intercept for this one would be 3. The way we get that, we'll plug in 0 for y. So x-intercept is 3. Likewise, the y-intercept is also 3. So there is that equation. And we'll see how accurate this turns out to be. X-intercept, so plug in 0 for y. X-intercept is negative 1. Y-intercept would be 1. And there is our second line. And then, of course, the solution is where these two intersect, which looks like pretty close to 1, 2. All right. So that's how we can do these. There are other methods too, and you really could just graph them and figure out the solution that way, or you can do it this way. You don't really have to do both, but you can. So let's look at the next one. We have x plus y equals 3, and 2x plus 2y equals 6. Now what do we notice here? If we divide this one by 2, we get x plus y equals 3. And that is the same equation as that one. So these are actually the same equation. So what does that tell us? It tells us, so this would be this line where the x and y intercept are both 3. And so these are the same lines. So we actually have infinitely many solutions. Infinitely many solutions. If we want to write these as parametric solutions, we could let y equal t. And then x would be 3 minus t. And the way we get that, just solve y is t. So move the y over here, get x equals 3 minus t, or 3 minus y. So now just plug in any real number for t, and then do 3 minus that real number, and that gives you the ordered pair that will satisfy this line. So all the points on this line are going to be solutions to this system of equations. All right, then the next one. So this one, notice that this is the same on this side, so x plus y and x plus y, but these are not the same. So what does that tell us? That tells us that, and maybe we can graph these and see what it tells us. So we already know x plus y equals 3 is going to look like this. X plus y equals 1, so now find the x and y intercepts, and they're both going to be 1. So 1, 1, and it's going to look like that. So what, and if you graph this on a computer, not handwritten, what would you see? These two are parallel lines. And of course, that tells us that there is no solution. So no solution here. Okay, so hopefully that's mostly review. I'm sure you're very familiar with these. All right, so the number of solutions of a system of linear equations, we either have one solution, and this tells us that it is a consistent system, or we could have infinitely many solutions. This would also be a consistent system. So all we mean when we say consistent is there is a solution, at least one. So you either have one or you have infinitely many, and then the last possibility is no solution. And in that case, it is inconsistent. So an inconsistent system has no solution. Okay, so let's look at this one. Now here we have 3 variables, and this is where you got to start being careful. It's very easy to make a mistake somewhere, and you probably want to have a little system for doing this. Eventually what we want is we want one of the equations to only have one variable. And I typically would say get rid of these. And so how would you do that? How would you get rid of this one? And just take them one at a time. How would you get rid of this negative x? Well, let's call this the first equation. Let's call this the second equation, and this the third equation. And so let's add the first 2 equations. Oops, let's not circle the plus. 1 plus 2, and we're going to replace 2 with that. So let's write the first equation just as it is. Let's write the third equation just as it is. We're not going to change. And so now if we add 1 and 2, so x minus x, that's going to go away. Negative 2y plus 3y, it's going to leave y. 3z plus 0 is going to leave a 3z. And then 9 minus 4 is going to leave 5. Okay, so these are equivalent systems as long as you don't make a mistake. They are equivalent systems. We'll talk about different things that you can do to these systems of equations that are equivalent as far as you go from one to the other. So it's kind of like if you have x plus 3 equals 6, you can add and subtract. Well, we'll add, although you wouldn't actually do this, but you can add and subtract the same thing on both sides. So these are equivalent equations. They have the same solution set. That's all we're doing here. We are just, this is a legal thing to do. Add two equations, then replace one of them with that new equation. So these are equivalent systems. And we'll talk about the legal things that you can do at some point. Now, let's try to get rid of this one. What can we do? Let's multiply the first equation by -2 and add it to the third equation. Then we're going to replace the third equation. So let's write first two just the way they are. And then let's add -2x plus 2x. That'll go away. -2 times -2y. That'll be 4y minus 5y. That gives a -y. Now, I would not be opposed to using a calculator on even though this is basic arithmetic. It's very easy, especially when you get to the negatives. It's very easy to make a mistake. I mean, I know you know how to add and subtract negatives, but it's very easy to make a mistake. So -2 times 3 plus 5, that gives us a minus z. And then -2 times 9 plus 17, that gives us a -1. Okay, so now we really have a system of two equations here, which you know how to solve. Let's kind of divide these. So now, how can we get rid of this one? So you notice we're getting rid of that -x, which we did. We got rid of that. We're going to get rid of the 2x, which we did. And we're going to get rid of the -5y, or now it's a -y. So let's add these two equations. So let's do equation 2 plus equation 3, and that's going to replace equation 3. X minus 2y plus 3z equals 9. Y plus 3z equals 5. And then add these two. So y minus y is 0. 3z minus z is a 2z. And then 5 minus 1 is 4. All right, so now we are where we need to get. So now we got rid of that one. So now we are where we need to be. And where do we need to be? Why do we get to this spot? Well, we have this equation with one variable. We have this equation with two variables. We have this equation with three variables. So now we can just back substitute. So this one clearly tells us that z equals 2. Then let's substitute 2 in here. So y plus 3 times 2 equals 5. And that tells us that y equals -1. Maybe circle these as we go, just so we don't lose it. Now we have x and y and z, but we already know what y and z are. So we have x minus 2 times -1 plus 3 times 2 equals 9. So let's do x plus 2 plus 6 equals 9, and x equals 1. And that looks like it is correct. So our solution, we'll write this as an order triple, 1, -1, 2. So write the answer, the ordered triple, or however many you have in the same order you have here. Now, if you had a fourth equation, which I think in the homework you do have one with 4, you would do the same thing. So we'll put a W here. It doesn't really matter what it is, but then you have W, X, Y, Z. So now you would need to get rid of all of these three W's plus, so you're just making this little triangle on the bottom. So you have the main W, X, Y, Z, and then you're going to get rid of this triangle just in the same way that we did here. But now you'll have an extra couple of steps when you have 4. All right, so then let's look at a picture of this. So here we have a picture, and obviously probably not going to be able to draw this on your own, but just to kind of give you an idea of what this looks like in 3 dimensions. So when you have 2 dimensions, 2 variables, you just have a 2-dimensional plane and you have lines. And wherever those lines intersect, that's your solution. When you have 3 dimensions, now we're in a 3-dimensional plane. So you have X and Y, but then you have this Z plane. So imagine this one's coming out of the board, out of the screen here. So X, Y, Z. And so now instead of lines, we have planes. So these equations will make planes in 3 dimensions. Now, how can planes intersect? Well, just imagine you have 3 sheets of paper. How can you make them intersect? It's a little bit hard because sheets of paper can't go through each other like we're trying to do here. So what this tells us is that these 3 planes are intersecting at this 1 point, 1, -1, 2, which should be right there. So it looks kind of like they're overlapping a lot, but in actual fact, they're not. So if you pick 2 of them, they're intersecting in a line, but then those 3 intersection lines are just intersecting in one spot. So not super important if you can visualize this. It's more important that you can maybe more important that you don't even use the picture, but just in case you like the picture, there it is. And that's kind of what's going on. What is going on? Of course, when you get to 4 dimensions, then who knows what that picture looks like. But all right, so I think that's enough for this one. We will pick it back up in section 1.2.